We live in a world that feels pretty solid and predictable. I mean, a cat is either here or there. A light switch is on or off. Simple, right? But underneath all of that everyday reality, there's another one, the quantum world. And it's a place that is just pure mind-bending weirdness. So how do we get from one to the other? How does the universe build our normal, classical reality from a foundation that's so bizarre and uncertain? That's the huge mystery we're going to try to solve. Honestly, this is one of the biggest questions in all of physics. It's like the ultimate cold case, the mystery of the missing quantum weirdness. And look, this isn't just some philosophical head-scratcher. Cracking this is one of the biggest roadblocks to building amazing future tech, like quantum computers. So in this explainer, we're going to put on our detective hats, follow the clues, look at the evidence, and see if we can finally crack this case. All right, so here's our crime scene. On one side, you've got the quantum world, where a particle, say an electron, can literally be in multiple places at the exact same time. It's called superposition. Its whole existence is just a wave of possibilities. But then on the other side, you've got our world, the classical world, where a cat is in one spot and one spot only. A choice is either A or B, never both at once. These two descriptions of reality just seem totally at odds with each other. So where does all that quantum strangeness go? To solve this, every good detective needs to know what kind of evidence to look for, right? We have to find the unique fingerprint that an object leaves behind only when it's acting in a truly quantum way. And that definitive clue, that smoking gun, is something called wave interference. Just think about ripples in a pond for a second. When two of those ripples cross over each other, they create a new, really distinct pattern. Well, in the quantum world, particles can act like waves, so they do the exact same thing. If a particle is in superposition and goes through two slits at once, its probability waves interfere with each other, creating this telltale pattern on the other side. This interference pattern, that's our quantum fingerprint. And this quantum fingerprint isn't some rare, exotic thing. Scientists have found it all over the place in the microscopic world. I mean, just look at this list. They've seen it with photons, electrons, entire atoms, neutrons, even really complex molecules, and these weird states of matter called Bose-Einstein condensates. It is the absolute signature of quantum behavior. Okay, so we have our fingerprint, this interference pattern, but just finding it isn't quite enough. To really crack the case, we need a way to measure just how clear and strong that evidence is. We need a kind of forensic tool to put a number on the quantumness of a system. And that tool has a fancy name, interferometric visibility. I know it sounds a little complex, but the idea behind it is actually super simple. It's just a number that tells you the contrast of the interference pattern. Basically, it's a rating for the quality of our fingerprints. Is it a clear, undeniable print, or is it just a blurry, useless smudge? The calculation itself is actually pretty elegant. All you do is take the maximum intensity of the pattern, that's the brightest part, and subtract the minimum intensity, the darkest part. Then you divide that difference by the sum of those two. That simple ratio perfectly captures the contrast, giving us a hard number for how good our evidence is. And this table here shows you exactly what that number means. If the visibility is high, so it's getting close to 1, it means we have these sharp, high contrast lines. That's a crystal clear fingerprint. The quantum behavior is strong and undeniable. But if the visibility is low, close to 0, the pattern is all washed out and blurry. The evidence is weak, or maybe it's gone completely. The quantumness has vanished. So, this brings us to the most crucial question of all. What is causing our clear quantum fingerprint to get smudged and totally erased? What force turns the weird quantum world into our boring old classical one? Well, we have a suspect. And the name of our culprit is decoherence. This quote from the physicist Juan Pablo Paz really gets to the heart of it. Decoherence happens when the surrounding environment basically finds out what state the quantum object is in. The second a record is made, the moment that information leaks out, the quantum game is over. So here's how the crime goes down, step by step. It all starts with our quantum system just chilling in a state of superposition, say a particle going through two slits at once. But then it interacts with its environment. Maybe it bumps into an air molecule or a photon of light hits it. That tiny interaction leaks information about the system state, like which slit the particle actually went through. That creates a record out there in the environment, and the instant that record is made, poof, the superposition collapses. The particle is forced to pick a side, and our beautiful quantum fingerprint is wiped clean. Okay, we've identified our culprit, decoherence. We know its method, leaking information into the environment. Now let's connect it all back to our original mystery and see how this finally solves the case of our two different realities. So here's the absolute key. Our classical world isn't fundamental. It's an emergent property. It bubbles up from the quantum world because of decoherence. The solid, predictable reality we all know and love isn't a different set of rules. It's just the result of quantum rules being constantly policed by the environment. The environment is always watching, always measuring, always forcing those quantum possibilities to collapse into one single classical reality. So just how powerful is this policing from the environment? How fast does it actually erase all that quantum weirdness? Well, the numbers they're almost impossible to even think about. For any object you can hold in your hand, the rate is just staggering. For an object that's just 1 gram, sitting at room temperature, the rate of decoherence, the speed at which its quantumness gets erased, is about 10 to the power of 40 times faster than the rate it loses energy. I mean, that number is so huge, it's practically meaningless. What it really means is that for any object big enough for us to actually see, its quantum superposition is destroyed almost instantaneously. The environment is just too noisy, too interactive for that quantum weirdness to ever survive on a large scale. So there we have it. We've pretty much solved the mystery. The classical world we see is born from this relentless process of the environment constantly monitoring and erasing quantum effects. So let's just wrap up with what this all means for us and how we think about reality itself. All right, here are the key takeaways. First, our classical reality isn't a given. It emerges from this deeper quantum level. The mechanism for that is decoherence, where the environment acts like this huge, non-stop observer, forcing quantum systems to pick a state and stick with it. This is the reason you'll never see your cat in 2 places at once. It's just too big and interacts with way too much stuff. And this isn't just philosophy. It's a massive, practical headache for scientists trying to build quantum computers because they have to protect those fragile quantum states from being destroyed by this very process. And that leaves us with one last really fascinating question. The line between the quantum and classical worlds isn't some sharp divide. It's a process, a constant negotiation with everything around us. So if the reality we actually get to see is just the result of information leaking out, it makes you wonder, what other, stranger realities are hiding just beneath the surface, lost in the noise before we ever get a chance to see them? What else are we missing?